of linear equations. When we talk about equations with two variables, it's important to understand that every equation in two variables has infinitely many solutions in the form of ordered pairs. So for example, let's look at the equations x plus y equals 5 and x minus y equals 1. Here, we can see that all of these ordered pairs make that equation true. 1 plus 4 is 5, 2 plus 3 is 5, 3 plus 2 is 5, and 5 plus 0 is 5. And for the other equation, x minus y equals 1, 8 comma 7 makes it true, 3 comma 2 makes it true, 1 comma 0, and 0 minus negative 1. And we could come up with infinitely more of those. We could just generate one after another. But the only point that will make both of them true is the point 3 comma 2. It satisfies both. If we look at that pair of equations together, think of them as a single problem. It's called a system of simultaneous equations. And when we say we want to solve it, that means we want to find the ordered pair that will make both of them true at the same time. The process of finding the solution of a system of equations is just called solving the system. However, sometimes you may hear it said as we want to find the point of intersection. In that case, it's important to remember that you're looking at two lines, and we're looking for the ordered pair where the lines would intersect on a graph. When you have two lines, there are several possibilities. First off, maybe the lines intersect, and if they do, they can only intersect in one spot. That is called a consistent and independent system. If the lines are parallel, they never intersect at all, and we say that that system has no solution. And that's usually referred to as an inconsistent system of equations. Finally, the third possibility is that maybe the two equations really represent exactly the same line. They're just different forms of the same equation. In that case, they're usually called coinciding lines, and that system is referred to as consistent and dependent. So the first situation here has one solution, and it will be in the form of an ordered pair, x comma y. The second situation has no solution. The two lines never intersect because they're parallel. And the third situation has infinitely many solutions. And when we come to that point, we'll talk a little bit more about how to write that as a solution if you happen to get that for an answer. Okay, so now we would like to talk about the different methods for solving systems of equations. Certainly you could look at them on a graph and you could approximate where they intersect, and if they're integers, you could even graph them and find that point of intersection. But we would like some algebraic and analytical methods for solving them. You'll probably remember these from both Algebra 1 and Algebra 2. Let's look at the substitution method first. In this method, we solve one equation for a variable. We're just going to say in this case, just for the sake of an example, we're going to say we're going to solve for y, but you could just as easily solve for x. We'll substitute the expression obtained for y for every y in the second equation. So we'll make a substitution there. Then we'll solve the single variable equation that results, and that will give us one of our answers, either the x or the y, depending on which of the variables you have substituted for. Once you have one of the coordinates of your answer, you can substitute that coordinate into the very first step and find the other coordinate. And that's how the substitution method works. Let's look at an example. Let's take the system of equations 3x plus y equals 1 and negative x plus 2y equals 9. And let's solve it by substitution. We have four options here for how to start this problem. We could solve the first equation for x, or we could solve the first equation for y. It's just important that we isolate one of the variables. Likewise, we could solve the second equation for x or y. Now, we want to choose one that's going to be easier for us to solve. Not that these are particularly difficult to solve for either variable. However, if we have a coefficient of positive 1, that's always going to be the easiest thing to solve for because it'll be a single step. So look at this first example, the very first equation here, and notice that the y has a coefficient of positive 1. So if we just move the 3x to the other side, we'll produce y equals 1 minus 3x. So we can very quickly solve that equation for y. And I like to put a little bubble around it just to kind of remember what I'm working with. And then we're going to take this quantity and we are going to substitute it into the other equation in the place of the variable y. So let's make that substitution. Negative x plus 2 times 1 minus 3x equals 9. If we distribute there, we have negative x plus 2 minus 6x equals 9, which is negative 7x plus 2 equals 9. So we know that negative 7x has to equal positive 7, and therefore x has to equal negative 1. So there's one of our coordinates. We know that these two equations intersect at the point where the x value is negative 1. Now we just want to find the y value of that point. Well, if I take that x value and I substitute back up here into my bubble, that will tell me what y equals. So y equals 1 minus 3 times the x value I found. So it looks like y equals 1 plus 3, which is positive 4. So the solution to this system of equations is negative 1, comma, positive 4, which means a couple of things. If we substituted those values into both equations, it should make both of them true. It also means if we looked at the graphs of those two equations, that should be the ordered pair where the lines intersect. So that's a basic example of the substitution method. There's a second method for solving systems of equations called the addition method, although most of us may know that by the name elimination method. It just kind of depends on what your book called it in Algebra 1 or Algebra 2. The first step here is we want to rewrite the equations of the system in a form so that the terms with the same variable are aligned vertically. We want all of the x's lined up over the x's, the y's over the y's, and the constants over the constants. Then we're going to multiply all of the terms of one or both of the equations by constants that are chosen deliberately to make the coefficients of the x or the y, it can be your choice, differ only in sign. So we want them equal but opposite. So if we have a positive 5x, we want a negative 5x. If we're trying to eliminate the y variable, if we have a positive 8y, we want to turn the other one into a negative 8y. So we need to get them equal but opposite. And we do that by multiplying through both sides of the equation by a number that we can just kind of make up. It can be any number you want and you can multiply by it. After we do that and get one of the variables equal but opposite, we add the equations together and solve the equation that results if possible. Meaning, it could be no solution, and we'll look at some of those along the way as well. But if it's possible, solve that equation. Then you will know one of your ordered pairs. You can take that ordered pair, you know one of the coordinates, and you can take that coordinate and substitute it back into either of the original equations and solve for the remaining variable. Then you'll know both coordinates and you'll know the final ordered pair. Let's take a look at an example. In this case, we have 3x plus 2y equals 8. So let's rewrite that down here. And 2x minus 5y equals 18. So technically, if I wanted to, I could eliminate the x's or the y's. Since the y variables already has one positive, one negative, I think I'll just go ahead and eliminate them. Okay, so right now I have a positive 2y and a negative 5y. If I want to produce the same coefficient, I can turn them both into tens by multiplying the top by 5 and the bottom by 2. and that would make my y variables have a coefficient of positive and negative 10, so that when we add them together, we would get 0. When I distribute, we have to be sure we distribute to both sides of the equation. So on top, we have 15x plus 10y is equal to 40. In the second equation, we have 4x minus 10y is equal to 36. Now that we have our y variables equal but opposite, we can add these two equations together, producing 19x, and see how those y's cancel, has to equal 76. If we divide both sides by 19, we can see that the x value of our point of intersection has to be positive 4. So there's one of our answers. Now we just need to find the value of y and we'll be finished. So we can pick either one of the original and we can substitute that into it. It doesn't matter which, so I'm just going to choose the first one. And I'm going to substitute into 3x plus 2y equals 8. Now that I know x has to be 4, I can say 3 times 4 plus 2y is equal to 8. 12 plus 2y is equal to 8, which means that 2y has to equal negative 4, and y has to equal negative 2. So there are the coordinates for a point of intersection. And remember always to write your final answer as an ordered pair. Positive 4, comma, negative 2. And if you have time, you should always go and check and make sure that it makes both of the equations true.